So, we see that two criteria need to be satisfied in order to get in order to get chromium carbide precipitation along the grain boundary. One, we have seen the carbon content, carbon percentage, it should be beyond 0.02%, and we have seen from the phase diagram that this is my phase diagram, this is temperature, this is percentage of carbon, and this is austenite plus carbide, and this is austenite zone. Now, there in between we have gamma plus alpha plus carbide. Now, if the carbon content, and this is around 0.02%, and if the carbon content is around 0.08%, then, and this is the solidus line, and if we cool it, and during cooling, let us say we are at this temperature around 700 degrees Celsius, and the 700 degrees Celsius, the chromium carbide precipitation is possible, and the amount of carbide that is to be formed will depend on the percentage of carbon that is available for carbide formation. And as you see that the carbon equilibrium carbon content at this temperature is this much, but the amount of carbon which is excess in the gamma solution is of this much. So, this much carbon is available for carbide formation, and the carbide would form along the grain boundary, since the grain boundary provides heterogeneous nucleating sites. Now, second case is, now if somehow if we while cooling, if we cool it very fast, and since carbide formation is a nucleation and growth kind of phenomena. So, if we do not allow sufficient time to form carbide in this zone, then of course, the whatever carbon what is there in the solution at this stage will stay in the solution even at low temperature, and the solution becomes supersaturated with carbon. And if we have very rapid cooling, we do not have sufficient time for carbide formation, and we do not have the problem of carbide precipitation along the grain boundary. So, time is important issue. The amount of time what we spend at this temperature zone around 600 to 800 degrees Celsius in this temperature zone, the amount of time spent would be a critical criteria, because if we spend lot of time, then carbide precipitation would be possible, since the time available for precipitation, nucleation and growth. And second issue is, if somehow, if let us say we are cooling it slowly up to this above 800 degrees Celsius, and then in this temperature zone we cool it very fast, and then after we cross this temperature zone, we see that we do not need much of cooling rate. Even if we go for a very slow cooling rate, it is not possible for the carbide to precipitate out along the grain boundary. So, we see that this temperature zone 800 to 600 degrees Celsius is also critical. So, time and temperature. So, time and temperature both are important in order to have carbide precipitation, and this temperature means the critical temperature zone, which is 600 to 800 degrees Celsius in case of 188 stainless steel with carbon percentage around let us say 0.08%. Now, another criteria could be there that is basically the other alloying elements. Other alloying elements, and not only other alloying elements, the alloying elements which are strong carbide formers. Strong carbide formers like niobium or titanium. See, if we have these highly carbide forming elements and if their affinity towards carbon is more than the chromium, then depending on whether then the possibility of having carbide precipitation, which is the chromium carbide precipitation, since chromium is important in giving stainless property. So, if we have these elements and if somehow we can take care of the excess carbon that is available in the material by forming niobium carbide or titanium carbide. So, chromium carbide formation, we do not have much of carbon left. So, chromium carbide formation would not be there, but that is what, depending on whether the this kind of alloying elements are present or not, the sensitize of this carbide precipitation along the grain boundary would be decided. So, these are the major criteria that are essential for carbide precipitation and preferentially chromium carbide precipitation along the grain boundary and leading to chromium depleted zone along the grain boundary, and that would give rise to intergranular corrosion, and that we have seen the mechanism we have already seen. Now, once we have these three criteria, let us see when I weld a stainless steel, 18/8 stainless steel, let us say that stainless steel when we weld, that time it does not have the problem of chromium carbide precipitation. Now, the point is, whenever we have two stainless steel bar, let us say the two stainless steel block, and I need to weld in this zone. Okay. When we weld, that time we have to raise the temperature around more than 1650 or 1700 degree Celsius in order to melt this local zone. Now, this is also 18/8 stainless steel and this is also 18/8 stainless steel, and let us say the carbon content is 0.08% and here also 0.08%. Now, let us say this two blocks, stainless steel blocks, they have no carbide precipitation along the grain boundary. So, the intergranular corrosion in these two blocks individually, they do not have this problem of intergranular corrosion, because the chromium carbide has not formed along the grain boundary in any of those blocks, and the chromium always stays in the solution. And let us say the heat treatment that has been followed would be such that the chromium carbide precipitation does not occur. How we can go for that heat treatment? We can quench it rapidly, so that the chromium does not form in this temperature zone. Sorry, chromium carbide does not form in this temperature zone. Fine, we do not have any problem. Now, the point is, if we weld, if we take the temperature to around 1700 degree Celsius, and then if we have a section, different sections, we can have a different temperature time profile at different sections, and depending on those profiles, we will see some of the sections there we have sufficient time for chromium carbide precipitation, as well as we can have this favorable temperature zone. And when we have, let us say, some zone, let us say in this block you have this section where we have sufficient time, sufficient time, and the temperature zone is 600 degrees Celsius to 800 degrees Celsius. So, chromium carbide forms in these zone only, other zones we do not have any problem. And when this chromium carbide forms, this is the grain boundaries, and if the chromium carbide forms along these grain boundary zones, along these zones, okay, so you have this chromium carbide formations. These are the chromium carbides, and you have a depleted zone. That time the steel is called sensitized. And the phenomena is called sensitization. Means where we do not have the problem of chromium carbide precipitation along the grain boundary, that particular steel, if we satisfy this situation sufficient time in the 600 to 800 degree Celsius zone, we can have the situation of reprecipitation of this chromium carbide along the grain boundary and leading to chromium depleted zone along the grain boundary, keeping the rest of the system where rest of the system intact, where the chromium in solution would be 18%. But along the grain boundary, the chromium content can go down to around 2% or less. So, you have grain boundary or intergranular corrosion, and that time this is called sensitized steel, and the process is called, or the phenomena is called, sensitization. Now, during welding of these two unsensitized block, that means there is no grain boundary precipitation of chromium carbide. Let us see what happens and what would be the temperature profile or time temperature profile as we go from this zone, the welded zone, to the body of the towards the body of this block. Now, let us say this is my welded zone, let us say this is my welded zone, and let me, what I can do, I can perform a simple experiment. What I can do, I can mark all those points, let us say this is one point, this is one point, this is one point, this is another point. Let us say this is D, this is B, this is C, this is B, this is A. And here you see the A is directly in the fusion zone, and rest of the thing are basically the heat affected zone, and that heat affected zone always is we experience while we do fusion welding. Now, since there are thermocouple fixed to these points, so we can easily get the temperature while heating as well as temperature profile while cooling. So, if we see this is time scale, this is temperature scale. Now, we can have a different temperature zones. Let us say this is 1200 4 degrees Celsius, this is 93, then you have 982, then you have 871, and this is in centigrade scale. This is 760, and this is 648, and let us say this is 537, and below that it is 315. So, this is the temperature scale what we are interested with. Now, when we see that the temperature while heating, let us say we are heating from here, and while heating if we employ very rapid heating, generally the temperature increases rapidly. So, in case of A point, at this point of course, this point would be the maximum temperature, which is the center of this weld zone, where the temperature go maybe around 1600 or 700 degrees Celsius, but in the fusion zone, at the end of this fusion zone, we can have a temperature profile like this. Temperature could be like this during heating. Now, when it cools down, since it's at the maximum temperature, this would be at the maximum temperature compared to the other points during the welding process. So, when it cools down like this. Now, let us say this is A, the temperature profile for the thermocouple at A point, which is the boundary between the end of the fusion zone and the heat affected start of the heat affected zone. Now, if we consider what is the temperature time profile for the thermocouple B, thermocouple at position B, we can have a profile like this. Profile like this. This is for the case with B. Now, then we have the zone, the thermocouple which is fixed at point C, we can also get the temperature profile like this. And then point D, of course, it would be the lowest one like this. So, this is point D, this is point C. Now, if you see these graphs carefully, you will see the temperature, the maximum when it cools down, this is heating, this part is heating, and this part is cooling. When it cools down, that time the temperature, the maximum temperature from maximum temperature around 1204 degrees Celsius, the cooling rate also would be very steep. Since we have a larger temperature, so large temperature differences, so the cooling rate also would be very steep. As you go down from the maximum temperature to this level, to this level, to this level, that means as you go away from the fusion zone, then you have the attainment of the maximum temperature would be, the maximum temperature would be less as you go down towards this side. So, that is what you are seeing, that B, thermocouple B shows this is the maximum temperature that can be attained at this point, and gradually if you go this way, the maximum temperature also would decrease. And as well as, since you have the lower and lower temperature gradient, you have sluggish cooling rate as we go down like this. Now, you see that in case of B, we have a particular temperature, let us say this is my 800 degrees Celsius, this is my 800 degrees Celsius, and this is my zone, this is 600 degrees Celsius. Now, the material of this zone, and C is basically the start of this 648 zone. So, this zone, actually this zone is staying in the sensitized temperature zone, which is 600 to 800 degrees Celsius for the maximum duration. For the maximum duration, if you see that this is the amount of time that the material is spending in this critical temperature zone where we have sensitization. But if you see the A case, the amount of time that the material is spending is only this much, only this much. So, the amount of time that is being spent in the critical temperature zone, which is 600 to 800 degrees Celsius temperature zone, when we have the thermocouple at this point, that is only this much time. And if you see in case of D, that is not at all reaching to the temperature zone, which is 600 to 800 degrees Celsius. So, that means we are bound to get more and more or possibility of having chromium carbide precipitation in case of this material of this zone. In this zone, we have more and more possibility of chromium carbide precipitation along the grain boundary. And here, though we have spent some of the time in this 600 to 800 degrees Celsius temperature zone, but the time is so short, it will not allow that chromium carbide to form. At the same time, it will not allow the chromium carbide to grow. So, we see that in this zone, we have the possibility of sensitization. And this material in this zone will get sensitized. This is the region where we have intergranular corrosion when it is exposed to corrosive, and rest of the material, and same way the other side also you can experience a particular zone where we have sensitization. So, this zone and this zone would be susceptible to intergranular corrosion, and rest of the zone will not be susceptible, and there will not be any problem. So, the failure would occur along this zone, and this is called, this particular section generally is called Weld decay. This particular process is called Weld decay. Weld decay, this particular process is called Weld decay, and this Weld decay means the creation of sensitized zone in the stainless steel, which is not sensitized when it was not sensitized before welding. So, before welding there was no sensitization problem, and after problem, because of this temperature time profile, we have a zone which is developed, and this is basically the area of Weld decay, and here we have intergranular corrosion, and rest of the cases we do not have any intergranular corrosion. So, that is what it is very important to have the time temperature phenomena, and in case of stainless steel we always prefer arc welding over gas welding, and that is also understood from this picture. If we have gas welding, the heating rate would be very slow, as well as cooling rate also would be slow, and there would be a large heat affected zone. So, we can have more and more area which would be susceptible to intergranular corrosion, and sensitization would be possible, or weld decay would be possible. But if we employ arc welding, the heating rate would be very sharp, at the same time cooling also would be very sharp, as well as the heat affected zone would be narrow. So, the effect of sensitization or weld decay would be minimized. Now, let us see, this is the problem with the welding of stainless steel, and if the stainless steel is not sensitized before welding, and after welding, because of this phenomena sensitization can happen, which is called weld decay. Now, let us see how many ways we can avoid this sensitization. There are major 3 processes by which we can avoid sensitization. Let us get into that processes, how we can prevent sensitization. One is, this is prevention or control of sensitization of austenitic stainless steel, and mainly stainless steel. So, first process is, since we have seen that if we can decrease the carbon content in stainless steel less than 0.02%, we will not have any problem of sensitization. And sensitization is related to the chromium carbide precipitation along the grain boundary. And if we do not have sufficient carbon which can be left out by the austenitic lattice during cooling in the temperature zone of 600 to 800 degrees Celsius, chromium carbide cannot form, because there is not much of carbon left for the chromium to take up those carbon and form chromium carbide. So, if we can go for very low carbon percentage, and if we can take the carbon content less than 0.02% or around 0.02%. So, that is basically low carbon austenitic stainless steel. So, we do not have much carbon to form, much carbide to form. So, very low carbon. So, this is one way, but this is a costly affair, since we need to employ secondary steel melting process where we can get rid of carbon in the steel, and it increases the cost of the material. But another problem with this, let us say we have a very low carbon content in stainless steel. So, that means I do not have any problem of sensitization. We can easily cool slowly in this temperature zone. So, if we cool very slowly in this temperature zone, and if we have a very low carbon, then we do not have chromium carbide precipitation and sensitization process. But the point is, if we let us say go for oxyacetylene gas welding, then since it is a very low carbon, the system can have a tendency to pick up carbon from the gas welding process itself. Okay. So, when it picks up carbon from the gas welding process, that means the flames, that time the carbon content again goes up to beyond 0.06 or 0.05%. So, little bit of carbon which is left out, and the same process would happen, and there could be a possibility of sensitization or weld decay because of this carbon pickup. Now, second case is we can have suitable heat treatment. Suitable heat treatment means somehow if we can, as we have seen the temperature, time or phase diagram. So, that case if we can cool it very fast in this temperature zone. If we cool it very fast, we do not have much time to form chromium carbide. So, there is no problem of sensitization. So, suitable heat treatment. And third is addition of carbide formers like niobium or titanium. What they will do? Let us say the carbon content is 0.06% in the austenitic stainless steel. Now, these elements, when it is basically made, these elements are added, and these elements are very strong carbide formers, and those can take up those excess carbon and it will form carbides, and that carbides may also form along the grain boundary. no problem. It can form inside the grain boundary, inside the grain, at the same time it can form along the grain boundary. And so, once the carbide forms, these carbides forms, so the carbon content in the solution or in the lattice goes down, or the iron lattice goes down, and then the carbon which is required for chromium carbide to form would not be available. So, then we do not have chromium carbide precipitation along the grain boundary or sensitization effect. Now, the point is, as we are saying that, as it is said that the titanium carbide or niobium carbide, they can also form along the grain boundary, but still we are not experiencing much of problem with the sensitization, much of problem with the grain boundary attack or intergranular corrosion. The main thing is, in case of stainless steel, 18/8 stainless steel, the corrosion resistance is coming from chromium. So, somehow we have to keep chromium in the solution. So, even if these are forming along the grain boundary, but still since the around the grain boundary zone also the chromium percentage is more than around 18% or close to 18%, we have complete protection. So, this is one issue, and now when you add these alloying elements and form carbides and take care of those carbons available for carbide formation, chromium carbide formation. So, this process is called stabilization. This process is called stabilization. Now, other two cases, they are not stabilization. The stabilization, whenever we say that the sensitized steel is stabilized, it always means that somehow the niobium or titanium carbide, titanium are added, and we have the formation of titanium and niobium carbide in the steel, and these titanium and niobium carbide, when they form, they do not allow the chromium to form chromium carbide, because not much of carbon is left out in the system to form chromium carbide. So, this is called stabilization, and these are the control mechanism in case of stainless steel in order to avoid sensitization. So, there are two important issues in case of stainless steel. One is sensitization, another one is stabilization. So, we can have these three protection mechanism. Now, the point is, even if sometime the material has low carbon, even if the material is, let us say, moderately low carbon, let us say 0.05 or 0.04% carbon, and also we have niobium and titanium presence there. So, the material, the stainless steel is stabilized still, but still we can come across sensitization phenomena. So, we will see one example, that is a classic example why the sensitization can happen even the material is stabilized. So, that can happen in case of stainless steel, stabilized stainless steel drum which handles fumic nitric acid. So, let us see that example. It is basically the sensitization of stabilized austenitic stainless steel. So, now if we have a drum, let us say this is the drum which handles fumic nitric acid, and this is handling HNO3 acid, and this is a thin sheet drum, and the drum is welded like this part is welded, and the drum can experience a very localized intergranular corrosion, very localized intergranular corrosion, and there could be failure of the drum. Along the welded zone, we can have a very sharp intergranular attack, and the drum can fail or break into pieces. So, this particular process, a sharp crack formation due to intergranular corrosion, in case of stabilized stainless steel drum, that is called, this particular attack is called knife line attack. This particular attack is called knife line attack, and that happens in stabilized stainless steel. And this is the problem which is associated with welding the steel sheet, and then subsequently when we anneal this steel in the temperature zone around 600 to 800 degrees Celsius, we come across this knife line attack. Now, why does it happen? If it is stabilized steel, it should not have happened. Now, this happens because of that after welding, when we go for stress relief operation, because it is a thin sheet, and when we go for welding, then there would be a lot of coincident strain, and that coincident strain is to be relieved, and when we go for stress relieving operation, then we come across sensitization, and that sensitization would lead to a very sharp zone which is sensitized, and that section would be corroded due to intergranular attack and lead to knife line crack formation or knife line attack. So, let us see situation what is happening there. Now, in case of this particular situation, generally this has been experienced in case of 347 stainless steel, which is 18/8 stainless steel with niobium addition. So, since niobium is added, which is the carbide former, strong carbide former, that is what we have the stabilization property. Now, if we come across a particular schematic plot, so we see the knife line attack happens in case of stabilized stainless steel of this nature, 347 variety, which is 18/8 niobium containing steel. Now, if we see a different levels where the carbides, different carbides can form, let us say this is the level which is around 1230 degrees Celsius, where chromium stays in the solution and niobium carbide forms. Now, if you come to 790 or let us say 800 degrees Celsius, in this zone we can have a situation where if there is a chromium carbide, there is chromium carbide in the system like this. So, chromium still it remains in solution, or even if the sensitized steel, let us say the sensitized steel is heated to high temperature beyond 800 degrees Celsius, the chromium carbide which can dissolve C6, and of course, there is a small change beyond this temperature, niobium carbide also dissolves, and it means that chromium always will be in solution beyond this temperature, and let us say if the steel is stabilized, That means, the stabilized steel already has niobium carbide. So, if we heat beyond this level, existing niobium carbide will also dissolve. Now, this temperature zone means chromium will be in solution, but if we have a situation like this Weld decay phenomena, there we have this zone where we have chromium carbide precipitation. Beyond this temperature zone, the chromium carbide will dissolve also. And in this temperature zone, there is one more phenomena, that is niobium carbide will form. Niobium carbide forms. Beyond this temperature, niobium carbide dissolves. Below this temperature and up to 800 degrees Celsius, chromium stays in solution, and if you are heating a stabilized steel beyond this temperature, there will be dissolution of existing chromium carbide, but if there is niobium presence in the steel, the niobium carbide again will form in this temperature zone. Now, let me get back to this graph again. If we see that I have plotted at 800 to 600 degrees Celsius, I have said in case of B, this is the time frame where I can have chromium carbide formation, and this time frame is very large. So, chromium carbide formation is possible. Now, there is a small change, this one should be like this. Why? I have changed from here to there. So, if we raise the temperature in the B point beyond this level, so this process would happen, the chromium carbide would dissolve. But if we have the temperature, maximum temperature around 800 degrees Celsius, then we would definitely have this much the time frame where the system temperature remains in this sensitized temperature zone. But if we consider in case of A, why we are considering that this much time is basically a small change. So, time would be this much would be the time. So, this much would be the time, this much would be the time where the A point is existing in the sensitized temperature zone, and this is a very short time. In that temperature zone, we will not have any chromium carbide precipitation. Now, if the system has niobium carbide, and then if we heat it like this, up to 1200 this point, niobium carbide will remain as niobium carbide. And if the niobium carbide remains as niobium carbide, and beyond this temperature zone, chromium carbide would dissolve if there is any chromium carbide. So, that means, if the steel is heated beyond this temperature zones, niobium carbide would dissolve and chromium also would remain in solution, and if we are in this temperature zone, chromium would be in the dissolved condition, and if there is any trace of chromium carbide, that would also dissolve and niobium carbide would form. And if the temperature zone is 600, in this temperature zone, if we cool it very slowly, so dissolved chromium would again form chromium carbide. But if we already have niobium carbide, then chromium carbide would not form, because we do not have any carbide, do not have any carbon to form chromium carbide, and below this temperature zone, no reaction. So, let us see what happens in case of stabilized stainless steel. In case of stabilized stainless steel, we have niobium carbide plus no chromium carbide. So, this is my condition. Now, I have during welding, I have heated the material from room temperature to the melting temperature or beyond melting temperature. And once we take it to the melting temperature, everything dissolves, because we see that beyond 1230, niobium also goes into solution, chromium also goes into solution. So, everything would be in the dissolved condition. So, whatever advantage what we had due to the formation of niobium carbide would not be there, since everything has gone into solution. So, the carbon is available for chromium carbide formation, but of course, the steel has to go through these temperature zone where we have possibility of carbide formation, chromium carbide formation. Now, since this is a very thin sheet of metal, and if we go for arc welding, the cooling rate would be very fast. And if the cooling rate is very fast during cooling, so during cooling it will go like this, and if the cooling rate is very fast in this zone, niobium carbide will not form. So, if niobium carbide would not form, then I do not have the stabilization because of niobium carbide formation. But the point is, since the cooling rate is also very fast, so in this zone also cooling rate would be very fast. So, that means very short time would be the material would exist in this temperature zone. So, no chromium carbide formation, and the steel has gone to this place where we have no niobium carbide and plus no chromium carbide. So, if the steel, even if the niobium is present in the steel, because of this very rapid cooling due to a very thin cross section of the stainless steel plate, we have no niobium carbide, no chromium carbide. The system will not experience any intergranular attack. Why? Because we do not have the situation where the chromium depletion is happening. So, we have no chromium carbide formation and no chromium depletion. So, this is not a sensitized steel. Not. Now, the point is, since this is a thin sheet metal, so after welding we always go for stress relieving operation, because there will be a quenched in stress. So, if we go for stress relieving operation in this temperature zone, so in this temperature zone we see that even if niobium is present, niobium carbide cannot form. So, in this temperature zone niobium carbide cannot form, but chromium carbide can form. So, once we have chromium carbide formation, and the chromium carbide always will form along the grain boundary, so the material would become sensitized. So, once we take it to this level for stress relieving operation, will come across chromium carbide precipitation along the grain boundary, and we can the material, the steel would become sensitized, and where? In the narrow zone. In the narrow zone of that welded part would become sensitized, and there would be a sharp intergranular attack and a sharp crack formation, which is nothing but knife line attack. So, it is actually this process, this entire process which is the knife line attack situation, is basically happening due to sensitization of stabilized stainless steel and the stabilization, the sensitization is happening because the niobium carbide and chromium carbide both dissolves, and because of the rapid rate of cooling, niobium carbide does not form in this temperature zone when the material is cooled down in this temperature zone, and chromium carbide even does not form, but due to stress relieving operation after welding, we always come across this chromium carbide formation if the stress relieving operation is carried out in this sensitized temperature zone. So, we can experience chromium carbide formation on the grain boundary, and the material would be susceptible to intergranular attack, and that attack would be very sharp in nature because of gas welding or because of the welding process what we are carrying out, that is the arc welding process. That means, the heat affected zone would be very narrow, and the situation this weld decay portion would arise very close to the weld decay zone, very close to the welded zone, as well as this section would be very sharp because we have a very rapid cooling, and only this part, this section would experience this sort of stress, this sort of chromium carbide formation. So, this is happening even, and that time even if we have niobium, we do not get any advantage of niobium. So, this is a typical condition for sensitization of stabilized stainless steel. So, this is about intergranular corrosion of stainless steel, 1880 stainless steel. This can happen in other material also, as we have already cited some example. For example, impurity segregation, that is iron segregation along the grain boundary of aluminum alloys, or zinc enrichment along the grain boundary in case of brass. And there could be the possibility of sensitization in case of stainless steel and weld decay, and the weld decay we have already explained how weld decay happens, and the heat affected zone, the narrow band of metal where we always experience the temperature, the material is in the temperature zone, which is basically most critical in terms of chromium carbide precipitation for a longer duration, and that time we experience chromium carbide precipitation along the grain boundary, and we have chromium depleted zone, and that chromium depleted zone would go for preferential attack along the grain boundary, and there could be a possibility of intergranular corrosion. So, this is about intergranular corrosion. Now, let us get into one more process or one more form of corrosion, that is called dealloying process. Dealloying, or there are different names, or selective bleaching, or de-zincification in case of brass, or graphitization, or denickelification, like that. It means that let us say you have A and B, these two elements are mixed and they are in solid solution. And when they are in solid solution, and if it is exposed to corrosive solution, that time depending on the electrochemical potential of individual elements or the nobility or activity of any of the elements, the noble metal will stay back in the solution in the material, and the active metal would go into solution preferentially. So, that means if B is active metal and A is noble, that time B always tries to go to the solution or electrolyte preferentially, leaving A in the material. So, this is basically the preferential dissolution of B. Like that, in case of brass, let us say alpha brass, which is 70-30 copper, 70-30, 70 is copper percentage and 30 is zinc, copper zinc alloy, we experience that for a long exposure of this alpha brass to potable water, that time we experience that some portion we have a reddishness. The reddishness of the some portion of that particular material increases. And if we do composition analysis of that part, we will see that zinc content has gone down, even it can go down to less than 5%, and the copper content in that around that zone, this is zinc, this is copper. So, copper content can go beyond 90% from 70%. So, here we see the zinc is dissolving preferentially, leaving the copper in the material. So, copper content increases and zinc content decreases, and the system over the surface we will see the reddishness increases. So, that redness or the surface become more and more red colored, and also if we see the structure of it, that structure becomes porous in nature. So, this is a particular example where zinc dissolves preferentially, leaving copper in the material in the brass. So, this is called dezinkification. And graphitization is another phenomena which can happen in case of grey cast iron. This can happen in case of grey cast iron, where iron dissolves, leaving the graphite flakes in the body of the grey cast iron. So, this is graphitization. This is a sort of misnomer. Graphitization means that graphite formation from in case of cast iron composition, graphite formation is basically the graphitization, and then denickelification is nothing but in case of copper nickel system, we can experience nickel dissolution, preferential dissolution of nickel, and copper content in the alloy increases. So, this is basically the dealloying, which means the one of the element goes into solution preferentially, or selective leaching, that means one of the material is leached out, one of the elements in the alloy is leached out because of this process, corrosion process, or dezinkification, zinc goes into solution preferentially, denickelification, nickel goes into solution preferentially, or graphitization, iron goes into solution preferentially, leaving the graphite flakes in the body. This is basically the dealloying or selective leaching.